Welcome back to Math 103. This is video number 16 on voting. This video is actually something of an afterthought to our discussion of voting methods and fairness criteria. There is a mathematical link between this chapter and the next one that we're going to need to understand later on, and that is to understand the answer to the question, how many different preference ballots are possible with a certain number of candidates. So we have now studied elections with 3 or 4 candidates, and to begin to transition to the next topic in the course, we consider how many different preference ballots are possible. In other words, how many different ways are there to rank the candidates on a single preference ballot if there are n candidates. Don't be intimidated by that letter n. Okay? It just means however many candidates there are, we can call it by the letter n. So we can make the observation that if there are 3 candidates, then there are 6 possible preference ballots. So if the candidates are called A, B, and C, then we can list all of them, and it doesn't take too long to list all the different ways of ranking the candidates. There are 6 of them, and for reasons that'll become clear in a little bit, we're going to write that 6 as 3 times 2 times 1. Now, there is a special notation for writing such a product of integers as 3 times 2 times 1. In other words, start at 3 and decrease 1 integer at a time until you reach the integer 1. The special notation for 3 times 2 times 1 is 3 followed by an exclamation point, which you might think says 3! But in fact, it is read 3 factorial. Thus, 4 factorial equals 4 times 3 times 2 times 1. That's just what 4 factorial means. When you compute that, it's 24. 5 factorial equals 5 times 4 times 3 times 2 times 1. When you compute that, that's 120. And we can keep going 6 factorial, 7 factorial, etc. Worth noting, it's worth remarking, that 4 factorial, 4 times 3 times 2 times 1, can be thought of as 4 times this whole thing. In other words, 4 times 3 factorial. So 4 factorial equals 4 times 3 factorial. Similarly, 5 factorial equals 5 times 4 factorial. So what is the connection between factorials and the number of different possible preference ballots? All right, I claim that if we have 4 candidates, then there are exactly 4 factorial, that is 24, different possible preference ballots. If there are 5 candidates, I claim that there are 5 factorial different possible preference ballots. And indeed, we can say the same thing for any number of candidates. If there are n candidates, however many n is, then n factorial, I claim, is the number of different possible preference ballots. Now, why does this make sense? Why is it true? I've made a claim, but why is it true? Well, we've already seen the first step here, that in the case of 3 candidates, we've seen just by listing them that there are 6 different possible preference ballots, and 6 is indeed 3 factorial. Great. Right. So far, so good. But now what happens if we introduce 1 new candidate to this election? So we go from 3 candidates to 4 candidates. Now how many different preference ballots are possible? Well, let's reason this out in the following way. So if D joins the election as a candidate, where could we put D? Where could we insert D onto a preference ballot? Well, you could get a bunch of new preference ballots by putting D as the first choice. In other words, take that block of 6 different preference ballots that have just 3 candidates, A, B, and C, and we get a bunch of 4 candidate preference ballots where D is in first choice all across the board. Well, there's no reason D has to be only first choice. Well, we also get 6 more preference ballots, another block of 6 preference ballots, this time with D inserted in second choice. What just happened? We've just found 4 blocks consisting of 6 preference ballots each. So that produces a total of 4 times 6, so 6 plus 6 plus 6 plus 6, different preference ballots. So in other words, 4 times 6, but 6, remember, is 3 factorial. So 4 times 3 factorial, but that's just 4 times 3 times 2 times 1. That's 4 factorial, right? We've just counted the total number of preference ballots with 4 candidates, and that's, it turns out, 4 factorial. Okay, so there are 24 different possible preference ballots with 4 candidates. Well, by the principle that if you liked 4, you've got to love 5, I can ask, what does the same line of reasoning tell us about taking all our preference ballots with 4 candidates and introducing a 5th candidate? Okay, now how many different possible preference ballots should there be? So we have in front of us now all 24 different possible preference ballots with 4 candidates. So think for a moment, and pause the video, think what would be the analogous thing to do when we introduce a 5th candidate, E. What would be analogous to what we did previously when we were first introducing D? When we introduce a new candidate, E, we could write E into the first choice position of every one of our 24 preference ballots here. That would produce a block of 24 preference ballots that all have E as first choice. But we could get another block of 24 preference ballots, each of which has E inserted as second choice. And similarly, we could get another block of 24 preference ballots with E inserted as third choice, another 24 blocks with E inserted as fourth choice, and yet another block of 24 ballots with E inserted everywhere in fifth choice. The punchline is that in an election with 5 candidates, we have just reasoned out why it should be that there are 5 copies of 4 factorial ballots. There are 5 blocks with 4 factorial preference ballots in each one. How much does that come out to be? Well, 5 times 4 factorial, 5 blocks of 4 factorial ballots each. That's 5 times 4 times 3 times 2 times 1. Okay, that's 5 factorial. That is 120 different possible preference ballots. So we have a process of reasoning that explains why it makes sense that there are 5 factorial different preference ballots possible when we have 5 candidates. By continuing to use the same reasoning, we can go on to 6 candidates, 7 candidates, any number of candidates. And any number of candidates is what we mean by n candidates. If you already have all n-1 factorial preference ballots for only n-1 candidates, then putting one more candidate in to bring you up to n candidates will multiply the total number of possible preference ballots by n. Right? You'll have n separate blocks of this many ballots each, and that will give you a total of n factorial possible preference ballots. Right? If that reasoning process mystified you a little bit, you can go back and rewatch the videos, but this is an important idea. Factorials are an important mathematical idea, and we're really going to need them in the next chapter. In order to check your understanding, please answer the following 3 questions. First, how many different preference ballots are possible if there are 10 candidates? How many if there are 20 candidates? And are these numbers surprising to you? So just pause the video and answer those questions and then continue. When there are 10 candidates, the number of different possible preference ballots equals 10 factorial, and this number is so large that most people don't believe it the first time they see it. You can ask your calculator to just compute 10 factorial directly, or you can write out 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. In the course of doing that computation, it does turn out that 3.6 million does equal 10 factorial. It does equal the number of different possible preference ballots, even though you might be surprised that only 10 candidates can produce that many different possible ways of ranking them. If you thought that was surprising, then 20 candidates are even more so. when there are 20 candidates, there are 20 factorial different possible preference ballots, and 20 factorial is approximately equal to 2.43 times 10 to the 18th power. In other words, the true value of this number is obtained by taking this decimal point and moving it 18 positions to the right. We've also done some rounding off here, but the point is that this number is in the quintillions. Right? That is almost unimaginably large. Many students are surprised when they see just how vast these numbers are, because it seems as though 20 candidates should not generate an utterly vast number of different ways of ranking them. But in fact, they do. And this will be a very important idea in some applications in the next chapter. Congratulations on reaching the end of voting theory.